and make a quick video on task 7.4. This is going to be talking about different rules of integration. So right now we're looking at question number 5 and 6. They both use this same graph. So question number, let's zoom out a little bit. This is again number 5 and also number 6. They're using the same exact graph. So we're given this integral, and I want to remind you that integral means area under the curve. That's kind of the main idea here, but I like to think of it more as area between the curve and the x-axis. So let's start by looking at each individual region. So I'm going to mark out this first integral right here. This is the area under the curve between 1 and 3. And the linear function 2x minus 4 has already been graphed for us, so we're just finding that area between 1 and 3. So if I kind of draw my line between 1 and 3, this would be the area that we are blocking off. And let's just go section by section. When I'm looking at this one right here, I can calculate the area of this little triangle right here. 1/2 base times height. My base is 1. My height is 2. So it's just 1 unit, but because it's underneath the x-axis, it's -1. So let's do the same for this little piece right here. 1/2 base times height, which is 1/2, same base, same height. And because it's above the x-axis, it's a height of +1. So if I wanted to just say the total area from 1 to 3, I have -1 and then a +1. This is going to end up being just 0. Okay, let's move on to the next one. The next one is saying same exact linear function, 2x minus 4, but now I want the area between 3 and 8. So again, here's 3. And here is 8. We want this total area right here. So if I think about breaking it down, I like breaking it down as this rectangle right here and this triangle right there. Let's shade it in a little bit better. So you could do this as a trapezoid, but I generally just like go back to rectangles and triangles because I know those pretty quickly. So this rectangle right here, I could count the squares, or I could just do length times width. That's going to be 1, 2, 3, 4. Oops. 1, 2, 3, 4, 5 by 1, 2. 5 by 2, you could count those squares. That's going to be 10 units. And then our area of this triangle is 1/2 base times height. The base, we've already counted that out, is 5. Again, that's just the difference between 8 and 3 if you want to think of it that way. And the height would be then the difference between 2 and where this intersects up here at 12. So my height is 10, and I could count that out also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1/2 times 5 times 10 is going to be, let's get that back together, 25. So combined, our area of 25 plus 10, this area right here is going to be a total of 35 square units. And then let's do the last piece of this. The last piece is the integral, or again, the area between -2 and +1. So here is our -2, here is our +1, and once again, this is a great opportunity to use a little rectangle and then a triangle on top of it. If you wanted to use a trapezoid, you could do that as well. In fact, I'll do a trapezoid this time just to show you it's the same thing. The area of our trapezoid is 1/2. One of the bases, meaning one of the sides that's not proportionate, and the other base, again the other side where it's slightly longer, times the height or the width. So our first base is 1, 2, 3, 4, 5, 6, 7. Our other base is 1, 2. And our height is 1, 2, 3, 4. So this becomes 7 plus 2 is 9. 9 times 4 is 36. Cut that in half. I believe that's 18 square units right there. So 18. But here's the main idea. Because this is below the x-axis, it is not a positive 18. It is a negative 18. It is a negative 18. So let's kind of recap this. Here we have our negative 18. Here we have a little negative 1. Here we have a positive 1. And here we have a positive 35. We can combine those all together to find the total area under the curve for this function. So I'm going to leave that up to you guys to figure out. I'm going to leave that up to you guys to find the final answer. But if we look at this as a whole, I'm really just finding the area from this first x value right here at negative 2 all the way over to this last x value right here at 8. Again, negative 2 to 8. So I could actually write this as just one integral. One integral. I could write this as the integral from negative 2 all the way to 8 of this standard function. We haven't changed the function. We haven't done anything differently. And we're just adding the different regions. So yeah, it makes sense to say that if we can break this into individual pieces that all connect, we can just make it one combined integral. Okay, so that's question 5 and question 6. Again, I didn't actually tell you the total area. You're going to have to do that by combining these numbers right here. But this is your answer to number 6. Can you write it together as just one combined integral? There it is. The smallest value is negative 2. The largest value is 8. And it was seamless. There were no gaps in between. So we can just write it as one integral. With that in mind, let's explore number 10 and number 11. So looking at number 10 here, we are told that we have this one integral from 3 to 10 of this unknown function. And this same function we know from negative 3 to 3. So I want to think of this just on the x-axis. Let's say we got something crazy going on here. It honestly doesn't really matter what it is. But we know, let's say this is 3. From 3 to 10, we know this area right here. That's this first piece. And we also know this second piece. Somewhere over here, let's call this negative 3 all the way up to 3. So I know every single thing seamlessly from negative 3 all the way to 10. If I know everything seamlessly from negative 3 to 10, well, I can just say negative 3 to 10 f of x is equal to it, f of x dx. So this is essentially what we just saw with number 5 and number 6. If I can kind of piece these all together and they just seamlessly connect, well, I can write it as one integral starting at negative 3, ending at 10. And let's try one more, number 11. Again, I'm going to think about this in terms of a number line. That kind of helps me out. This time I'm not going to draw in a function. I'm literally just going to mark out my numbers. Let's call this 1, 2, 3, 4, 5. This one's 6 here. This very first integral right here tells me the area from 1 to 6. So let's pretend it's just some curve. I can do that better. It's some curve here. And knowing the area from 1 to 6 means we know all of this area right here, or it's symbolizing that area there. Well, I want to subtract out the area from 3 to 6. So this right here would be our 3. I want to subtract out the area from 3 to 6. So what is left over? That's what it's asking. It's asking you what is left over. Well, this right here is all that's left over. This little region right there from 1 to 3. So I can say that this is equal to the integral of 1 to 3 f of x dx. It's the same as kind of just looking at these boundaries right here and figuring out, well, I have 1 to 6. I know 3 to 6. What's left over? 1 to 3. Okay, I hope that helped out with just a short video to kind of get you guys rolling on these properties of integrals. These are called definite integrals. I feel the need to write that out for you guys. These are called definite integrals. Let me write that out. Definite integrals. So I've posted a video or two on these, but if you're looking for maybe some more resources, that might be something you want to look up. I hope to see you guys in office hours, period 2. Your office hours are on Thursday at 11 a.m. Period 3, your office hours are on Friday at 9 a.m. If you do not have a conflict with your period 2 or period 3 class, feel free to drop in on both. Hope you guys are enjoying calculus so far, and I'll see you then.